All right, ladies and gentlemen, 3 o'clock. Welcome back to your favorite class. Rawr. Only one announcement. That simulation number 2 is due on Tuesday. 2 times Tuesday. Can I get a hoo-ha 2 times Tuesday? Yeah, simulation 2 due on Tuesday, which is Cinco de Mayo. So if you want to throw in some pictures of like maracas or something for your simulation, that would be awesome. All right. So here we have another student submitted meme for today. Hopefully you enjoyed it. Thinking about stuff you can make as an engineer? Oh, that's pretty awesome. Doing actual engineering homework? Yeah, makes me want to cry. I had this like epiphany when I was in undergrad also. It's like, oh, I want to be an engineer. I can make all sorts of cool stuff. And then you realize you get to engineering school and you only do like 5 minutes of actually making things and then a bajillion minutes of doing ridiculous math and homework. So sorry if that one hits kind of close to home for everybody, but yeah, that is kind of the reality of engineering school. You're supposed to do like extracurricular stuff to make stuff and be on formula teams and RAR and all that. David Mai, before class or midnight for the simulation? Before class. So, I mean, 3 o'clock for you guys on Tuesday. Okay? So, get it done. 3 o'clock to my mailbox. Rachel Cole will probably get it right at 3 o'clock. She's a pro at that. Yeah, 3 o'clock to my mailbox. If you haven't started the simulation, do it. Okay? The geometry is complicated. So, do it. The handwritten portion, the geometry, crazy. Ask Caleb. He'll tell you. Without further ado, time for some dynamics. Let's continue our discussion of linkages. Caleb Foster. It sucks. Yes, it does. Do it anyway. Rawr. Math is hard. Linkages. Remember, we had linkages, and remember what linkages look like. So just to kind of jog your memory, we're looking at what generally looks like something like this. This is the most generic linkage that you could think of. And we said that analyzing these with traditional kinematics is annoying. And as soon as we start adding links to this, it's going to be more annoying. So, easier way, but we need complex math. And so we had a lesson yesterday on complex math and how we might define position, velocity, and acceleration using complex notation. So that's a quick review, and we'll remind ourselves. The complex vector notation takes place in the complex plane, where the complex plane looks a lot like your traditional Cartesian coordinate system, just like XY coordinate system, except now we replace the x-axis with the real axis and the y-axis with the imaginary axis. So now if we have, let's say, 2 points that exist, here's point A and here's point B, and we want the position vector that locates point B from A. Let's say that that is this vector here, the position vector which locates B from A. Then in traditional coordinate system, if we know that the angle here with the horizontal is the angle theta, then if the magnitude of this position vector is equal to capital R, then we have the position vector which locates B from A is something like R times cosine theta I hat plus sine theta J hat. And everyone's happy. The world is good. And when we move to complex notation, it ain't that hard, right? All we have to do is replace the I direction with the value of 1 and replace the J hat direction with the J variable, which is, recall, the imaginary unit. So here, RBA, this is still the same magnitude R, except now we replace the I direction with the unit vector representing the real axis. So this is like cosine theta times 1 plus sine theta times the unit vector representing the imaginary direction, which is J. where remember j is equal to square root -1. We use j in this class because your book uses j. I guess that's not the best definition or the best reason why, but that is what we do. So this was our complex vector notation with real and imaginary components. We can rewrite this using Euler's formula. And if you took anything away from lecture yesterday, I hope you took Euler's formula away. And that is that e to the j theta is equal to cosine theta plus j sine theta. With that rewrite, we have that the position vector locating B from A is the magnitude of this vector, r e to the j theta. And this was our most simplistic complex vector notation. Is that an oxymoron? Simple complex notation. All right, specifically for a position vector. All right. So there we were. A position vector that locates B from A is the magnitude of that vector multiplied by e to the j theta, where theta is the angle that that vector makes with the horizontal. Now, this looks a lot like polar coordinates, and so if you've got a lot of experience with polar coordinates and you like polar coordinates, then this should look comforting to you or similar in scope to polar coordinates. So now we want to move from position vector to velocity. So for velocity, we take this guy and we take the derivative with respect to time. So the time derivative here. And the time derivative of this guy is easy. That's why we write it in this particular notation, because the derivative of an exponential is simple. So then we have the velocity of B relative to A is the derivative of this guy, which looks something like Rj e to the j theta. And by the chain rule, there's a theta dot hanging on the back end here. So this was the velocity vector. And here we have the magnitude, r times theta, which looks a lot like r omega. So that's your magnitude. And then our direction is given by all of this mumble jumble here. All right, so this is your direction. So it is a vector. It has magnitude and direction, though it doesn't look like a traditional vector that you might be used to. Take one more derivative for acceleration. So we could then write that the acceleration of B relative to A, after doing this derivative, looks something like r theta double dot times j e to the j theta minus r theta dot squared e to the j theta. And this was our complex vector notation for the acceleration of this particular piece, the acceleration of B relative to A. All right, notice here that this also has magnitude and direction. Here is your magnitude. Here is your magnitude. And here is what would define your direction. All right. So there's that. You can also notice in this particular equation that there are flavors of things that you saw with your kinematics. What do I mean by that? You can also see here that this guy here is representative of something like, looks like alpha cross r. Okay, so the magnitude of alpha is theta double dot, magnitude of r is capital R. And this looks like what is omega cross r. So remember, the magnitude of omega is theta dot. The magnitude of r is capital R. So we have capital R times theta dot squared, which would come from that particular component. So we have this tangential term and this centripetal term that still pop their heads up. Though it looks funky because it's in this complex vector notation, I promise you that everything is there, right? So that was the lesson that we went through yesterday. All of these things will be useful when we go towards looking at the analysis of our linkages. So let's dive in on linkage analysis. Right, meow. now back to linkages. And remember what our linkage looks like. This here is a 4-bar linkage. And in this class, we're going to stick with analysis of 4-bar linkages. You look at this and you say, what the F? This has only 3 links. Why is it called a 4-bar linkage? Well, it's kind of a nomenclature thing. And the linkages that we have here in this particular piece are obviously, this is link number 1. This is link number 2. This is link number 3. And by convention, the way that we define the 4th link is the link that exists between the 2 fixed points. So we have to imagine that there's like a 4th link in this system that exists between these 2 points, and that is link number 4. So when I said 4-bar linkage, there's this imaginary 4th link. All right, so 3, I'll say free links, and 1 fixed between pins. All right, this is a 4-bar linkage, right? Usually with these linkages, we will assume we know the following about the link. We'll assume we know the link lengths. We're going to know the angle of first link. So that is the angle that this particular link makes with the horizontal, this angle theta. All right, we're going to assume that we know what that is, usually because that particular link is being driven by a motor. All right. We'll also assume that we know angular velocity and acceleration of first link. Right. The reason that we can assume that we know these things is because usually first link is driven by a motor of some kind. All right, so what I mean is this link in the chain, this guy here, is usually driven by some motor. And if you remember back to our examples before, we saw that to be true with kind of the motor example from way back in the day, which was here. So remember one of the linkages that we did way back in like week number 3. In this situation, we had that exact scenario. We were assuming that this link AB was being driven by some motor. So we knew that this had some angular velocity here that was given in the problem. And we're also given its particular snapshot in time of what the angle was of this particular position vector RBA. All right. So that's how most of these systems work. And you'll notice here that this is a 3-bar linkage that is being used to drive this piston system, right? So that is that. All right, now go away. Go away. Goodbye. All right. So that's the idea. This is like a physical representation of what's happening. Now we actually need to come up with like a mathematical model for what this looks like kind of theoretically so that we can start to do some analysis on it. All right. So this is the physical system. Bang. Now we need a model. And that model of the system is going to be based in our real and imaginary coordinate system. All right. So down here at the bottom, this is where our first fixed point is assumed to be. Right? We have another fixed point over here where everything ends up connecting. And then we have these arbitrary links that are in space. And the way that we're going to define these positions or these links in space is with position vectors. All right, so if we go back up to this, like just general linkage over here, and say here that like this is point A, and this here is point B, then we can define in space the points A and B appropriately. And we're going to define them in some generic general position. So we can see here that we'll have some position vectors, like let's say here's a vector that locates A from B. We have a position vector that locates B from A. And we also have a position vector that locates B from this last final link here as well. All right, so these are all the vectors that we're going to use to kind of like do our analysis. So let's give some actual names to these guys. So let's say that this first vector here, that's kind of going from the first origin to point A, is the position vector. By nomenclature, this is R2. And I'm going to try my best not to be annoyed, but whoever came up with the standard nomenclature for these linkages is just a dumbass. Okay, there's no other way to put it. Whoever defined how to define these position vectors and how to go through this nomenclature was just a freaking moron. So apologies for how these variables are defined, but they're horrible. So this is position vector 2, which locates A from this general origin. Here is position vector 3, which locates B from A. We have here, by nomenclature, position vector number 4. And you're asking, well, where's position vector number 1? Well, that is the position vector that locates the fixed secondary point from the fixed first point. So here we go here. This is the position vector R1. Why they did it this way, the world will never know. So here are these position vectors. I told you that we're going to assume that we know what the link lengths are. And by nomenclature, the links have the following lengths. The position vector R2 has link length little a. Oh, God, terrible. All right, the position vector R3 has link length little b. God, it just makes me laugh. The position vector R4 has link length little c, and the position vector R1 has link length little d. Why? Like, why would you do it this way? Why does position vector R2 not have length little b? And like position vector R3 have length little c? It just makes no freaking sense. Whoever did this was just for like on crack. I don't know what's going on with this. But this is the way that it is. All right. So let's talk about it. The position vector R2 magnitude is equal to little a. Position vector R3 magnitude is little b. Position vector R4 magnitude is little c, and the position vector R1 magnitude is little d. Obviously. Okay. We also have to define some angles for these guys. So the angle at the horizontal with this particular link is theta 2, because it corresponds to R2. The position with the horizontal of this link here is theta 3. It's because it goes with R3. Position from the horizontal of this link here is theta 4, and that's because it goes with R4. And we'll also make one last note here is that the position vector R1 has theta 1, which is always equal to 0. So this is always true. All right. So there we go. This is our model of what is this general linkage here. So any 4-bar linkage that you can create, this is your general model. Let's take a look at that homework problem from way back. Let's go in the Wayback Machine and let's look at this homework problem. Don't try to write this down. I'm just going to talk through it. Here's the homework problem from the Wayback Machine. This is, in fact, a 4-bar linkage. Okay, you'll notice some strange things about this. All right, this particular pin, as it's viewed in this image, is not on the same horizontal plane as this particular pin, right? So if you were actually going to do the analysis of this guy, you'd have to, can I do it here? You'd have to rotate this link in space. I don't know if I can do it with this actual pen. Can I do it with this pen? I'm going to try, damn it. All right, can I rotate? How do I rotate? I can't rotate. But you get the idea, is that you'd have to rotate it so that the pins were on some plane that looked like this, where this was your real axis, and here then this would be your imaginary axis. So if you wanted to do a 4-bar linkage analysis on this guy, you could do that. Where here this is like your R2, this guy is R3, this guy is R4, and then this guy is R1. All right. All that stuff. Here we go, and goodbye. So that's what you might want to think about doing. Oh my gosh, what happened up here? Oh God. I lost it. No. Okay. Don't worry, I got it back. So now let's take a look at this in a little bit more depth, and you'll notice that by vector algebra, the following is true. R2 plus R3 is equal to R1 plus R4. So the way that we've defined these vectors, you have this R2 plus R3 getting you to this location B. That's going to be equal to R1 plus R4 getting you to this location B. So this is just standard vector algebra. Rearrange to R2 plus R3 minus R4 minus R1 equals 0. We can write these guys using our complex notation. We have the following. R2 has a magnitude of little a, so it'll be little a e to the j theta 2. Obviously, a goes with theta 2, clearly. Plus R3 has a link length of b, e to the j theta 3, minus c e to the j theta 4, minus d e to the j theta 1, all equal to 0. We know that theta 1 by the definition of our little model here. We have the situation where the angle between these two fixed pins is equal to 0. So if theta 1 is equal to 0, that means this term is what value? If you say 0, I'm going to be irritated. This guy goes to 1. E to the 0 is 1. Don't write e to the 0 as 0. Don't be a freshman, all right? You're not a freshman anymore. E to the 0 is 1, since theta 1 is equal to 0 degrees, all right? We write a e j theta 2 plus b e j theta 3 minus c e j theta 4 minus d equals 0. Here's our expression. All right. Let's substitute back using Euler's formula. To dive in on this a little bit deeper. With Euler's formula, we have a times cosine theta 2 plus j sine theta 2 plus b times cosine theta 3 plus j sine theta 3 minus c cosine theta 4 minus plus j sine theta 4 minus d equals 0. All right, this is a vector equation. Notice that we have a real portion and an imaginary portion. So this is actually two equations. It's like I and j components, okay? We have real and imaginary components. The real components look something like this. A cosine theta 2 plus b cosine theta 3 minus c cosine theta 4. Let's make it clear that there's like a multiplication sign here. It's kind of difficult to tell. C times cosine theta 4 minus d equal to 0. Also, we have the imaginary portion, which is a sine theta 2 plus b sine theta 3 minus c sine theta 4 equal to 0. Notice that this particular portion doesn't have any imaginary component. All right. So hopefully we can sort of see that there's no sort of like J hanging out for that like fourth link, or what would be the first link, which is related to D, which makes no sense. All right. So we have these two equations, and this comes from the vector equation above. Let's recall what we have available to us. We know the following. Can I slide this over? Yes. We know link lengths. That is A, B, C, and D. We're going to assume that we know what those are, that those are provided. All right. We also, what's known as the driving angle, which is theta 2. These are all the things that we know. So if we know theta 2, we know all the link lengths. The only unknowns in these series of two equations are the values of theta 3 and theta 4. What does that correspond to for our particular linkage? All right. So in this particular linkage setup, we know link length A, link length D, link length B, link length C. We know all of those things. Right? You got the links. They're physical links. They are whatever length they are. Right? You also assume that we know this driving angle here, theta 2, because we're assuming that that first link in the chain is being driven by some motor. Okay, that's just the general assumption. What we need to solve for then is what is the angle of this third link in the chain, and what is the angle of this fourth link in the chain? Right? That's what we're looking for. How are the other links positionally related to the first link, given some information about the various link lengths and the driving angle of that first link? Right? So need theta 3 and theta 4. All right. Fortunately, we have two equations and two unknowns. Unfortunately, these equations are freaking complicated. Okay. So here's like equation 1. And here's equation 2. Who wants to go through those equations and solve for theta 3 and theta 4? Yeah, I don't. Dang, that would be so much algebra. All right. Lots of algebra. I'll cut to the chase. People smarter and more patient than me have done this. And so you have two equations, you have two unknowns. You can solve one equation for one of the variables, plug it into the other equation, solve for the variable, and you're going to get stuff that pops out. That stuff, complicated. Mostly because these trig functions and then working with other trig functions together with some constants floating around, not fun. Okay, not my favorite exercise. This is like the little girl in the meme crying over her homework. Oh, this is horrible. All right. So let's cut to the chase. And here we're going to solve for theta 3 and theta 4. Are you ready? Here we go. Two solutions possible for each of theta 3 and theta 4. You'll see that there's a quadratic equation that pops up in the solutions for these particular guys, and that's just the way that this ends up working out. Okay. So there will be a quadratic that forms. You guys hear like the guy revving his engine outside? Annoying. So the solutions that result start with theta 3. And like I said, there are two solutions. That's why I'm doing as theta 3, subscript 1, and subscript 2 for the two possible solutions that form. Here it's going to be 2 times Tuesday. No, I'm just kidding. Hoo-ha, 2 times Tuesday. All right, 2 times the tangent inverse of the following expression. Opposite of capital E. Yes, this is an E. Plus or minus square root of capital E squared minus 4 times capital D times capital F. Don't worry, this will all make sense in a moment. All over 2 times capital D. All right, there's your solution for theta 3. I'll define these constants E, D, and F in just a second. Similarly, for theta 4, could have 1 or 2. Like I said, there's 2 possible solutions. 2 times inverse tangent. God, this guy needs to go on with his car, man. It's annoying. Opposite of B, plus or minus square root of, everybody say it with me, B squared minus 4AC all over 2 times capital A. All right. So there are your solutions for theta 3 and theta 4. Cumbersome and annoying. You're going to ask then, what are these variables, A through F, and what do the two solutions of theta 3 and theta 4 correspond to physically? Okay, so those are the questions that you should have in your head. All right, we'll get to that in a second. Let's define what these variables A through F are. And I told you that algebra was annoying. You're about to see how annoying. All right. Cosine theta 2 minus, yes, a new variable, K1 minus K2 times cosine theta 2 plus K3, where we have the following. K1 is equal to little d on little a. These are link lengths, little d and little a. K2 is little d on little c. Okay, so these are link lengths, little d and little c. And then we have here K3 is this crazy thing. Link length A squared minus link length B squared plus link length C squared plus link length D squared all over 2 times link length A times link length C. Just what you thought it was going to be. Capital B, negative 2 times the sine of theta 2. That one's easier. Capital C. You guys are used to capital C. Oh, burn on your grade. Oh, I'm just kidding. K1 minus K2 plus 1 times cosine theta 2. And this is plus K3. And remember, these definitions of K1, K2, and K3 kind of feeding into this expression over here. All right, so those are A, B, and C, which are used to feed into the solution for theta 4. And then you also have capital D, capital E, and capital F, which feed into the solution for theta 3. To look something like capital D as cosine theta 2 minus K1 plus K4 cosine theta 2 plus K5. Capital E is the same as capital B, which helps a little bit. -2 sine theta 2. And then last but not least, you have capital F, which you guys are all very familiar with. Oh, just kidding. No one in this class is getting an F. Come on. K1 plus the quantity K4 minus 1 cosine theta 2 plus K5, where we have to define here now K4, which is equal to D on B. And then K5 is also another kind of crazy expression, and that is C squared minus D squared minus A squared minus B squared, all on 2AB. I told you that algebra was not exciting, but here are the general solutions. All right. So these are things that help us define the positions of each one of these particular links. Yeah, this is the easier method. Yeah, imagine trying to do this with kinematics. It would be harder than this. Imagine, harder than this. Okay, yeah. So this is all the general algebra that feeds into these equations up here. And remember, what we're after are these angular values, theta 3 and theta 4, of which we have two possible solutions. So what does it mean physically now that we've gotten all those constants out of the way? What does it mean physically to define the values theta 3 and theta 4? That's because the linkages that we've shown and linkages that we've drawn, we've all drawn in what's known as the open configuration. But there is also a possibility for these linkages to exist in another configuration, which is known as the crossed configuration. And I will show you what I mean with a simple picture. We call them open and crossed. All of the things we've drawn so far are the open configuration. So if we go back up to our model, here's an open configuration. All right, the picture that we showed before, here, open configuration. So what would it mean to be in this crossed or closed configuration? Well, picture says, picture's worth 1,000 words. Bang. Here are open and crossed configurations. Let's take a look at this. What I showed before was the open configuration. Here is our link defined by the length A, which is our position vector R2. The open configuration would have the next link kind of in this portion here, and this link here. It's this generic system that I've shown and kind of what represents all the things that we've looked at so far. This is the open configuration. Everything is kind of open. Now, with the same driving link, the same value of theta 2, how we're driving the system, we could also have a situation that exists where these links cross over each other. And in that situation, we could have another configuration that's physically possible here. This is the crossed configuration. All right. So with the same driving angle theta 2, we could have the crossed configuration, which would give you this value of theta 4 and this value of theta 3, which are different, obviously, than this open configuration, which still has the same driving angle theta 2, yet now has different values of theta 3 and theta 4. So this is how we get two different solutions for each possible angle of theta 3 and theta 4. One for the open configuration and one for the crossed configuration. Right? Right? So there you go. The two solutions of theta 3 and theta 4 give these two physical configurations, this open configuration and this cross configuration. Now, we have to be a little bit careful with our math, and that is because you could imagine a series of links that I hand to you, and I tell you, make me a 4-bar linkage out of these links, and you could have a situation where it is impossible for you to construct a 4-bar linkage given those particular links. Let me give you an example. I'll say, need to be mindful of physical possibilities. So let's say I have this particular example where I give you a link or a series of links, and I say, okay, your distance from here to here. Hold on, someone just knocked at my door. I don't think it's important, but maybe it is. All right, sorry, real life problems. All right, let's continue. You could have this situation where there's this distance here that exists, this little d, that we know to be fixed. And let's say I give you 3 tiny little links that can't get you to point D. So I give you this particular link, this little link here, and maybe one more link here. There's no way that you can configure those links physically to get you out to point D. So here you have some link length B, some C, and some A, or something like that you're trying to put together and form into a 4-bar linkage, but it's impossible. You can't do it. All right. So we should have mathematically the situation where if I give you those generic values of those linkages, the math should tell you that the solution does not exist. That's what you would hope for. All right. And what I'll say is those impossible solutions are captured by the quadratic formula. If we go back up here and we look at these equations, which are dictating for us the angle theta 3 and theta 4, which exists for this particular linkage system, we can see that we potentially have imaginary solutions if this portion or this portion ends up being negative. If this e squared minus 4df is less than 0, we're going to have some imaginary solution. So we can capture this impossible physical configuration by observing an imaginary solution for theta 3 and theta 4. So let's look at what the possibilities are for theta 3 and theta 4. possibility number 1 is that theta 3 I, so 1 and 2, is not equal to theta 4 I, and both are real. This is your open and crossed configurations. All right, so that's possibility number 1. You solve these quadratic formulas, you solve for the angles theta 3, 1, and 2, and theta 4, 1, and 2, and you see that they're all real, none of them are equal to each other. Away you go. Open and cross configurations for theta 3, 1, matching theta 4, 1, and theta 3, 2, matching theta 4, 2. All right, another possibility. Theta 3, I, and theta 4, I, imaginary. If that is the case, no physical configuration of these links is possible. All right. There's one more possible solution, and this one's a little bit more subtle. And that is theta 3i is equal to theta 4i, and both are real. Okay, so this is this e squared minus 4df, that portion of the solution being equal to 0. That would be that idea. You can show through that algebra that if that is the case, then it must be true that theta 3i equals theta 4i, and they must be equal to either 0 or 180 degrees. Physically, what this looks like is that you have, again, these locations that are fixed here and here, and you have a configuration of your 3 links that maybe looks something like this. All right, so maybe here is link number 1. Here's link number 2. And then here is link number 3. This is the only possible answer if theta 3 and theta 4 are equal to each other. So here, theta 3 equals theta 4 equals 0 degrees or 180 degrees. All right, so that's your physical interpretation for the situation where the quadratic equation only responds back to one solution. There is no open and crossed configurations here. That's why there's only one solution, because there's no open configuration, no cross configuration. There's only this flat configuration. Okay, so that's what it means if you get that additional solution. All right, so that's it for the lecture today. Hopefully we learned something interesting about these linkages. We've really only talked about position at this point, and so starting with the beginning of next week, we'll dive into the velocity analysis for these guys, and things should start to clear up a little bit and become a little bit more interesting. So thanks for coming. Have a great weekend. Enjoy the weather if you can. It's supposed to be nice. Go on a hike. Stay away from other people, etc., etc. Take it easy.